because that acid when dissolved in water, you get the hydronium ion and an anion, of course. And when you dissolve the base, you get a hydroxide ion. Those are the signature motif for acids and bases. Now, there are some acids, they do not have the protons or hydroxide ion, but still they could be acids or bases. So that's where the conjugate acid-base theory came up, and those are given by Bronsted and Lowry. And so when you have an acid, after reacting with the base, it generates conjugate base, and base generates conjugate acid. So that's basically we have, and they're always pair. So for example, the last one, acetic acid, it's an acid, plus ammonia, which is base. You don't see anything, right? There is no hydroxide ion or anything. You can see the acid proton right there though, but not the base. Then react and make the acetate ion. So acetic acid converted to acetate ion, and that acetate ion is the conjugate base. And then we got the what you call ammonia, the base that is converted to a conjugate acid, the ammonium ion. And as we say, stronger the acid, weaker the conjugate base, and weaker the acid and stronger the conjugate base. Likewise, stronger the base, weaker the conjugate acid, and weaker the base, stronger the conjugate acid. Just they have inverse relationship. Inverse relationship. In other words,
Wait,
if you,
I have a question. I'm
Yeah.
sorry. Can I ask a question?
Go ahead.
Oh, okay. So my question is that you said the weaker the base, the stronger the acid, correct?
Yeah, that is correct. And I
And then it's the opposite.
and
then it's,
true. Mhm.
go ahead.
So let's say weaker the acid, weaker the acid, W, weaker the acid, and conjugate base, stronger the conjugate base, SC. Everyone okay? Weaker the acid, weak, WA acid. Weaker the acid, stronger the conjugate base. Is okay? Conjugate. So weaker the acid, stronger the conjugate base. Conjugate base, right? So let's say stronger the conjugate base. I'm going to write S is a strong conjugate base CB. Everyone okay?
Yes.
And stronger the acid, stronger the acid, stronger the acid, and weaker the conjugate base. Everyone okay? So it's opposite, right? Isn't it? It's opposite, exactly the opposite. Likewise, if you say weaker the base, that's a W, weaker the base, and we have a weaker the base, stronger the conjugate acid. Everyone okay? I am using the acronyms, okay? So strong, weaker the base, W, weaker, base, B, stronger, S, the conjugate acid. All right? Likewise, if you say stronger the base, and you have a weaker the conjugate acid, conjugate base, conjugate acid. All right, so remember this, okay? So these are the exactly inverse. Now let me ask you then this question. So if you have a sodium hydroxide, NaOH, all right, NaOH, and NaOH will give this OH minus. Is OH minus weaker the conjugate base or stronger the conjugate base?
It's weak, right?
Huh?
I said, wouldn't it be weak?
Yeah, absolutely, because sodium hydroxide is stronger the base. Exactly, that's right. Sodium hydroxide is strong base, therefore is conjugate acid. So OH minus is a weaker the base. That is correct. That is correct. Weaker the conjugate acid. Yes, that's correct. Likewise, let me give you HCl. So HCl. HCl will give you hydronium ion and also Cl minus. That's a Cl minus. So is Cl minus. So HCl is the acid and Cl minus is the conjugate base. Is Cl minus is a strong conjugate base or weak conjugate base? Cl minus is a strong conjugate base or weak conjugate base?
Weak.
Weak, very weak, excellent. Because HCl is a strong acid. So therefore Cl minus is a weak conjugate base. So remember this. This is very, yes?
So I mean, I guess the way you can look at it is since it has a minus sign, negative, you could always think that negative is weak, correct?
No,
Okay.
That doesn't necessarily mean that. No. But you have to remember how that this acid is strong or weak. And then you can compare its corresponding ion. For example, HCl is a strong acid, Cl minus is a conjugate base, and this is a weak. Exactly the inversely relationship. So remember, huh? All right. I move on to the next.
Wait,
Okay.
I have a question.
Go ahead.
Okay, so when you were doing NaOH dissociates into like the hydroxide ion, hydroxide is a base, right? So NaOH would be an acid, a strong acid.
No, sodium hydroxide is a strong base, and OH minus is a conjugate acid.
You gave NaOH to us in the list of strong acids.
So you see, this is the very interesting stuff in the sense. Let me give you like this way. Let me write it down. So NaOH, very good point here. Okay, NaOH plus H2O. All right, H2O. All right. So now you can make this one is Na plus, it's aqueous. I'm not writing it, aqueous plus OH minus. OH minus. All right. Now, and these are aqueous solutions, of course. So in principle, if you do the dissociation, this is a strong base, of course. Now, if we make some reaction with this one, let's say plus HCl, so NaOH plus HCl and equal NaCl, so Na plus Cl minus plus H3O. All right, H2O, or it will be H2O. It will be H2O. Now tell me, for the Cl minus and H2O, actually H2O, so not OH minus, you're right. So H2O coming from the OH minus. OH minus converting to H2O, and HCl is converting to Cl minus. So that means OH, sodium hydroxide is strong base, and it is converting to water, H2O. Therefore, H2O is a weak acid, not OH minus. Very good point. Very good point. Okay. All right. So H2O is a weak acid. Sodium hydroxide is strong base, converting to water, H2O. H2O is a weak acid. All right. Shall I go on? Shall I move to the next?
Dr. Data.
Yeah.
This is Jackson Burnkoff. I was here when you called my name. I just couldn't respond. My Wi-Fi was bad.
Yeah, you're fine. You're fine.
Thank you.
All right. Let's go to the properties of acids and bases now. All right. So these are physical properties. Consider two types of properties of acids and bases. One is called physical properties. Physical properties are usually just a physical, looking at it, color, taste, all sorts of stuff. So physical properties includes, but not limited to, acids and bases are usually colorless, odorless. Bases are slippery. Acids are sour in taste, and bases are bitter in taste. I think we talked about a little bit of this. Almost all common acids are liquid. All common acids are liquid. And many carboxylic acids are weak acid, by the way. Carboxylic acids are weak acids, and they are basically solid. And if you recall, the last time, I think last Friday, I think I promised you that I'll give you a list of the weak acids. So weak acids and weak bases. So weak acids, please write down in a box. So weak acids includes, because we have one right here, all carboxylic acid. Please write down all carboxylic acid. Carboxylic acids are organic compound. We'll talk about later on. Or carboxylic acid, or carboxylic. Oh my goodness, my writing is carboxylic acid. Or carboxylic acids are weak acids. Or carboxylic acids are weak. Carboxylic acids are weak acids. So weak acids are all carboxylic acids. For example, acetic acid. Remember, we talked about acetic acid. Acetic acid is vinegar. We'll talk about, we already know acetic acid is the weakest of all. It's the weakest among those acids that you get. It's the weakest acid. So weak acid. There are many. So all carboxylic acids are weak acid, remember. Okay. And inorganic acid like H2CO3 is the weak acid. H2CO3. You can have H3PO4, the phosphate. H3PO4 is also a weak acid. Please remember those, right? So all carboxylic acid, acetic acid included, and carbonic acid, phosphoric acid, they're all weak acids. All weak acids. Weak acids. So remember those, right? I think I told you at the time. I will give it to you. And let's be weak bases. Weak bases. There are not too many, but there are quite a many. Let's say NH3, ammonia. Ammonia is a weak base. Likewise, another one, all amines. We'll talk about later on. All amines. All amines. All amines. All amines are weak bases as well. Like all carboxylic acids are weak acids, all amines are weak bases. And ammonia is NH3, is a simple molecule, is also a weak base. And you can include the another one, H2O is always a weak acid, weak base, and also H2O is here weak acid. Water could be acid or bases, right? So please write down the list. I gave you the strong acids and bases, but I did not have the weak acids or weak bases. Please write it down. All right, let's continue the properties. So properties of acids and bases. Bases are colorless, odorless, usually not much. HCl has some pungent smell if it is highly concentrated stuff. Otherwise, acetic acid has some smell as well, vinegar, but not much. Bases are slippery, and acids are sour in taste, bases are bitter in taste, and on all common acids are liquid, and many carboxylic acids are solid. Those are weak acids. Acetic acid is liquid, by the way, but other carboxylic acids are always solid. All bases are solids, all bases, except the exception is ammonia, except the ammonia. So exception is right here, exception, right? Right now, exception is NH3, ammonia. Exception is ammonia. Ammonia is a gas. In principle, once you add the ammonia plus water, it will make the ammonium hydroxide, which is a liquid. Ammonium hydroxide is a liquid, but ammonia in general is a gas. So chemical properties, and those are the next one. Shall I move on to the next? Everyone has it, right?
I need just a little more time.
Okay, go ahead. So once again, ammonium, as I told you a little bit verbally, ammonia, once you put it water, NH3 plus H2O, it reacts with the water, and that makes you ammonium hydroxide, NH4OH, ammonium hydroxide. And ammonium hydroxide is a liquid. So this is the exception, right? Otherwise, all metal bases, metal hydroxides are usually solids. Ammonia, NH3 as it is a gas. That's a gas, right? That's a gas. Once you add with the water, it makes the liquid, this ammonium hydroxide, that's a liquid. That's also base. So these are the exceptions. So remember, right? In terms of the physical properties. Shall I move on? Yeah?
I'm good, thank you.
All right, let's go to these are the reactions. Must remember, okay? These are reactions are very important to win the test, of course. So metal, this is general. The first line is general properties. Metals plus acids, salts plus hydrogen. Always. Metals plus acids, salts plus hydrogen, gas. Metals plus acid. So metal plus acid, salt plus hydrogen, and that's always. Remember, always. Salt is I will talk about later on. So for example, sodium, group 1A, solid, plus nitric acid equals solution. Make the sodium nitrate. It's balanced, but sometimes not be balanced, right? Sodium nitrate is a salt. It's a salt. Plus H2O, a hydrogen, gas. And that basically comes out of the equation, comes out of the reaction. So if you take a test, so for example, if you take a test tube, add some acid, and then if you add some sort of metal, any kind of metal, like a copper, like a penny, if you add the penny, or a magnesium, or any kind of metal, if you put it there, and you can see the bubbles, and those bubbles are the hydrogen gas coming out from there. Likewise, magnesium, group 2 metals. So I'm giving one example from each group, right? You can have a potassium, lithium, so rubidium, etc., etc. They're same kind of reactions. Likewise, group 2, magnesium, You can do the calcium, strontium, barium, same kind of reactions. Plus, let's say HBr, hydrobromic acid. You get the magnesium bromide salt and hydrogen. Aluminum, group 3. You can also use gallium, indium, plus sulfuric acid, make the aluminum sulfate and hydrogen. Everybody okay, right? So metal plus acid, salt plus hydrogen. So hydrogen is a gas, it comes out from the reaction, and metals are, the salts are usually soluble. Some salts, but not all salts are soluble, right? We have the solubility rules. Next one, metal oxides. Metal oxide plus acid. So basically reaction to the acid to the metal oxide, that's basically, right? Metal oxide plus acid, salt and water. Water. So the difference is only water. Hydrogen, only the metal alone. Metal oxide makes the salt plus water. Salt is the common, right? Salt is the common. Example, group 1 element, lithium oxide, Li2O. You can use sodium oxide, Na2O, potassium oxide, K2O, right? Sorry, K2O, and plus HCl, 2HCl. You get the lithium chloride salt plus water, liquid. Likewise, group 2 elements, calcium oxide, magnesium oxide, strontium oxide, barium oxide, any kind of metal, group 2 metal oxide, plus sulfuric, plus phosphoric acid, for example, and you get the calcium phosphate solid, and you get the water. Okay. Likewise, aluminum oxide, group 3, we can take the gallium oxide, indium oxide, plus carbonic acid, for example, and you get the aluminum carbonate plus acid. So basically salt and water, salt and water. This kind of reactions would be there in the test somehow, one way or another. So you must remember general principle of acid-base acid, the reaction to the acids, metal plus acid, salt plus hydrogen. Metal oxide plus acid, salt plus water. I'm going to next one, it's okay? So if you get the metal hydroxide, that's a metal hydroxide. This is also known as neutralizing reaction we'll talk about. Metal hydroxide plus acid, salt plus water. Exactly the same as metal oxide. Metal hydroxide plus water, acid, salt plus water. Salt plus
Excuse me?
Yeah.
Can you go back for a second? Okay, thank you.
You're welcome. All right. So metal hydroxide plus acid, salt plus water. Example, group 1 element, group 1 hydroxide, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, any one, plus perchloric acid, HClO4, potassium perchlorate, salt, plus water. Barium hydroxide, group 2, you can use calcium hydroxide, magnesium hydroxide, strontium hydroxide, also those are solid, but still you can react with acid, plus sulfuric acid, barium sulfate, plus water. Likewise, group 3 element, gallium hydroxide, aluminum hydroxide, indium hydroxide, any kind of group 3 element hydroxides, plus nitric acid, for example. These are not balanced, by the way. These are not balanced properly, right? Some of them balanced, some of them not. You can balance it if you would like to, right? And then you get the gallium nitrate, plus you can use, if you want to balance it, you'll get 3 right here. 3 nitric acid molecule, and you get like this. The others are all balanced, I guess, yes. So gallium nitrate plus water. So same thing, right? Metal hydroxide plus water, acid, salt plus water. Metal oxide plus acid, salt plus water. You remember those, right? This reaction is also known as neutralization reaction. Why neutralization? Metal hydroxides are base, right? So acid plus base, salt and water. So basically the common principle here, acid plus base, base is the hydroxide, right? Metal hydroxide is the base, acid plus base is equal salt, that's your salt, right? Salt plus water, H2O. So that's called neutralization reaction. And this neutralization reaction has a very good application, and I'll come back to the application very soon. All right, so that's the metal hydroxide. So that's basically the reaction with the metals, reaction metal oxides and metal hydroxides. We're going to move on, okay?
I have a question.
Yeah.
Okay, so you said that metal hydroxides, it's a neutralization reaction because the metal hydroxide is a base.
Mm-hmm.
So is a metal oxide not a base?
Metal oxides are usually is a compound. It's a ionic compound. It is not considered as a base until you add the water. That's right. Remember our base. Remember our definition of the bases, origin of bases? Metal plus oxygen, metal oxide dissolves in water, makes the base. So that's basically it's intermediate, you can say. It's intermediate. All right, any other questions? All right, so let me, so salt plus water, this as I said, neutralization reaction, and you'll see very soon, like any kind of salt that you use, and as one general application in your stomach acid. We'll talk about it later on. So next one is the application of neutralization reactions. It has many applications. As you probably know, one of the most important application is our stomach. And many people, whenever you eat something, food containing acidic food or something that you get the acid reflux, right? Acidics. And so you have to neutralize it, right? So basically what happened, our stomach, once you eat the food, it dumps plenty of HCl, hydrochloric acid, plenty of, very strong. And if you look at the pH, it's about 0.1, 0.8 to 1.0, very acidic. And those what basically happen, whatever we food put in there in our stomach, and HCl is dumping from those the mucosal cells. And if you look at they have a villi, and they're dumping those HCl for digestion, and that will digest the carbohydrates, proteins, lipids, esters, lipids, etc., and generates plenty of small molecule. They'll be ultimately go to the large intestine. At that time, they have a sodium hydroxide to neutralize, and there's a valve there in between. That valve must close when those components pass it through. If there's some problem there, there'll be acid reflux, and that's basically the heartburn. And in order to get to get some relief from the heartburn, what do? You take the antacids, right? It's common. It's very physiological. Everybody has it once in a while. Some people are allergic to some food. Some people can generate some acids, and it is not a disease. But GERD is a disease to some extent, called acid reflux disease. But most of the time it is solved by the neutralization reactions. And if you add the milk of magnesia, many people probably have it taken, right? It's a magnesium hydroxide. Melox, and Melox is aluminum hydroxide. Mylanta, Tums, etc. And Tums has a calcium hydroxide, plenty of calcium hydroxide. So they're all hydroxide, in fact. So this basically those antacids contain calcium carbonate, and that's where it Tums. Remember that sometimes they can give the companies give the commercial, right? Thum, something like that. This is just a very interesting commercial as it is. Basically calcium carbonate. So once it is dissolved, for example, right here, so calcium carbonate, once it goes to the stomach, and if you have plenty of HCl, calcium carbonate plus HCl make the calcium chloride and carbon dioxide. And that's why we can see some burping, right? Because carbon dioxide comes out from your mouth. In some cases, if it doesn't come from mouth, it will come to other end anyway, right? So calcium chloride is salt, nothing wrong. Calcium chloride, we need calcium, and carbon dioxide gets out. So that's basically the neutralization reactions. Likewise, if you have a magnesium hydroxide, for example, you can have a magnesium hydroxide with a similar kind of reactions, which I did not put it there, right? You have a magnesium hydroxide, MgOH2, right? MgOH2 plus HCl. HCl is the R1. That's basically on the stomach. That's what we're not using any other acids. And that equal same reaction. You get the magnesium chloride, salt, and water. This is perfect. This is perfectly fine. Magnesium we need some, but not too much. If you have it too much, it will be excreted from any urine. So that's the magnesium hydroxide, the Melox. All right, milk of magnesium. Now we also contain some aluminum hydroxide. Aluminum hydroxide is the Melox. Aluminum, not that bad. Aluminum is not that bad metal. Aluminum hydroxide plus HCl, and that also give you aluminum chloride plus water. Likewise, sodium bicarbonate. Sodium bicarbonate also contains some antacids contain sodium bicarbonate. In principle, sodium bicarbonate people used to use it long time ago. In the earlier stage, earlier human means maybe let's say 10, 30, 50, 60 or 100 years ago, people used to use this one. It's called baking soda. And people use for cooking. At the same time, this could also neutralize the acid from the stomach. And it basically makes the sodium hydroxide and water and carbon dioxide. Sodium bicarbonate, it has some another side effect. Side effect in the sense it also generates locally some NaOH, sodium hydroxide. So if people take for a long period of time, that people may generate, those people may generate the ulcer. Ulcer is the hole in the stomach, right? So basically say it will start deteriorating the tissues. So that's why it has been stopped. But most of the cases, Melox, Mylanta, Thums, etc., are good for the neutralization reactions. All right. So that's the application of the neutralization reactions and application of some of the acids, and like vinegar, for example. As you probably know, the vinegar is the acetic acid. The vinegar is a trade name. Acetic acid is the chemical name, and that's a chemical formula. CH3COOH, and that H is the proton. That is your proton, H plus, and it basically dissociates in water, make the acetate ion. Acetate ion is very, very strong conjugate base. All right, acetate ion. So acetic vinegar, everybody knows, is used for cooking. It's also used for preservatives. Yes, it also kills the bacteria. Some kind of diluted solution, 33%, 30% solution, that can also kill some bacteria as well. All right, and as you know, the cooking, many people use you cook some chicken or some other things, right? Marinate, and you can do the marination. Marination, you can do the adding some vinegar to the meat, and then if you keep it for longer, few hours or so, it tastes good, right? Because what happened, there's it basically meat has a fiber, lots of protein there, and it hydrolyzes a little bit. So basically, it makes some kind of porosity where those our spices and everything can get in, so it will be tasty. That's what's really, right? So it's a cooking. So vinegar used for cooking, preservatives, and some other purposes, killing the bacteria, some kind of lower solutions. And as you probably know, some extent, many people also give the advertisement, many companies, in fact, and they can use to kill some germs and bacteria from the plants. So if you take the vinegar solutions and spray it to the plants, if you are doing the gardening, and if you see the plants are infected by the plant viruses, then you can kill those things as well. All right, so that's a vinegar. Boric acid, very, very ancient people used to use, well, I should say ancient means about 100 years ago, something like that. People used to use the boric acid as antiseptic, especially for the eyes. It is a weak acid, extremely weak acid, boric acid, and it could kill the bacteria and viruses. If some people used to get some infection in the eyes, you can see the yellow pus, and if you use a boric acid, rinse it with a very diluted amount, of course, and that could be killed. They can kill the bacteria, can get some relief. So that's antiseptic. People used to use it, not nowadays. Not nowadays. Nowadays we have so many other things. Just put some drops, etc., and you can get the relief from that. All right. Next one is the phosphoric acid, H3PO4. Phosphoric acid, we have a plenty of inside our cells. As you probably will see later on down the road also, the phosphoric acid will dissociate into phosphate ions, and that phosphate ion will easily maintains our pH inside the cells. So phosphoric acid also has some other uses in biomacromolecules, like proteins, enzymes. Then the phosphate group to the proteins or enzymes, they change the function of the protein enzymes because the phosphorylation. It can add the modified sugar, and you'll see that during metabolic processes. I'll show you some example. When we have a glucose is degrading, the first step is making the glucose phosphate. The phosphate group PO4 added to the glucose, make the glucose phosphate. And then the glucose phosphate ultimately will be degraded in down the road in the metabolic processes called glycolysis, right? So that's one function. Another function, the lipids. Many lipids are phosphorylated. Specifically, the lipids consist of several components. One component is called fatty acids. Another component is called glycerol. So they make an ester. Then it also added the glycerol. One of the hydroxyl group of glycerol will add the phosphate group. That phosphate group will add to some other components. It is a very complex molecule, and those lipids, complex lipids, are present in our cell membrane. So the phosphate is one of the most important ingredients for the cell membrane as well, when it is bound to the lipids, of course. And as you probably saw, the nucleic acid, I already showed you. the beginning of our classes, right? Beginning of the class, the first day probably. All the nucleotides, ATP, GTP, CTP, TTP, or DTTP, or UTP, etc., all those nucleotides contain the triphosphate. 3 phosphate groups are attached to that. All are basically adding the coming from the phosphoric acid, right? Likewise, the hydrochloric acid, HCl, we use plenty of it in stomach, digestion of food, proteins, carbohydrates, lipids, etc., etc. And HCl, too much of it, we have a trouble, right? It's called GERD, or gastric the acid reflux disease. All right. So that's so these are some application of acid. There are many other acids too, but these are the some sort of applied to our health to some extent. Okay. All right. Next one, applications of some bases. Not too many, but there are many bases out there, and you see some ammonia. NH3. Ammonia is one of the most important ingredient for making urea. Urea is a fertilizer. How many of you know urea? I think you should know. Does anyone know what is urea? Urea, yes. So urea is basically, you have an NH3, right? NH3 gas, of course, and you take the carbon dioxide, CO2, and I'm not balancing it, huh? You get this compound, H2N, all right, H2N, CO, NH2, NH2, all right, I'm not balancing it. And that's our urea, that's the urea. Does anyone know what's the application of urea? Why do you use the urea? It's a fertilizer. It's a fertilizer. The plants love it as a nitrogen source and some extent carbon source as well, but mainly the nitrogen source. These two nitrogens are basically utilized by the plants. Plants need lots of nitrogen, right? It's a nitrogen fixation. So fertilizer is just to make the urea, and urea is routinely used as a fertilizer. The farmers love it. Next one, ammonia could be used as a cleaning agent. As you probably know, whenever you buy some ammonia solutions from the if you can clean your glasses, windows, it is a little stinky. And not only that, if you in the health professional in the night, no offense to anyone, right? In the night, when the custodians are cleaning those the floors and bathrooms, etc., you can see the strong smell. That's ammonia. It's an ammonium solution. What does it do? It kills the bacteria, germs, etc. to make it make basically sanitation. So you use it for sanitations, right? Then you have a spirit of ammonia. Spirit of ammonia is the ammonium solution. So if some people is fainted, and then basically you just spray it a little bit to the mouth, to the nose area, and basically it will get the sense. All right, because what basically it has a strong smell. Ammonia has a very strong smell, very pungent, called pungent smell. Magnesium hydroxide, another base. 8% suspension is used as laxatives, commonly known as milk of magnesia. We talked about, right? It's used for the acid reflux disease to neutralize the acid, stomach acid, HCl, and it is also used to treat the wastewater in metal processing plants. That's a little bit commercial application. When they treat the wastewater in the metal processing plants, so such that you do not contaminate the river water or ocean water, etc., etc. Some companies do, some companies don't. They dump it as it is. And it is also used as a flame retardant. If there is in plastics, if you have burning plastics, don't add the water, because that will burn more. They basically use the ammonium hydroxide, the magnesium hydroxide to stop the flame. All right. So these are some applications. There are many other applications we are not going through, right? All right. So this is the application must remember. Those will be the test one or another, and those are the good ones, right? Next one is the buffers. Now, does anyone have any question for the applications of the acids and bases and reactions of acids and bases? Then I'll go to the buffers. Yes? All right. If not, so let's go to the buffers. So what is a buffer? What is a buffer? What are the applications of buffer? And what type of buffers we have, etc., etc. That's basically what we talk about, right? So definition of a buffer is solution containing weak acid and its conjugate base that registers the pH change on small amount of acid or base added to it. That's the definition of a buffer. Now you can say why we need to have a buffer. Let's buffers are the one. So if we have some specifically inside our blood and inside our cells, blood is floating through all over the body, and cells also have enzymes, proteins, etc., etc. In order to have a proper function of the blood, like hemoglobin, or the enzymes inside the cell, or proteins inside the cell, they must maintain a particular buffer pH, a particular pH. And how do they maintain the pH? The pH is maintained through the buffering system. Buffering system. And what is the buffer consist of? A buffer is a solution containing a weak acid and its conjugate base. Weak acid and its conjugate base that registers the change of pH on small amount of acid or base added to it. And how does it work? Basically, this is the acid, right? That's a weak acid. Let's say weak acid is called HA. HA is the weak acid. So HA plus H2O in water, and it dissociates. Weak acid, so it dissociates reversibly, like this way. And that's why I'm writing two-headed arrow. You get the H3O plus and A minus. So that's a weak acid, right? That's a weak acid, as I said. It's a weak acid. And this is our A minus is a conjugate base. Is a conjugate base. Conjugate base. Stronger the weak acid, weaker the conjugate base. Weaker the weak acid, stronger the conjugate base. Everybody okay, right? And it generates the hydronium ion because the proton is given to this. So what basically happens, if you have a, let's say HA, for example, let's say we have HA, and in principle it is converting to A minus. Everybody okay? It converting to A minus. And how does it convert to A minus? If you add a little bit of OH minus. So if you add a little bit OH minus, base, OH minus, and OH minus will be converted to H2O. Everybody okay, right? So that OH minus, the little bit amount of base, taking the proton, making the water molecule, and the conjugate base. Weak acid converted to conjugate base. This conjugate base can be converted to weak acid if you add a little bit of proton, H plus. So basically, what this cycle basically tells us, if we have a weak acid and a conjugate base solution, if you add some acid, if you add some base, it will make a conjugate base. If you add some acid, it will make the weak acid. So basically, the definition says a solution containing a weak acid and its conjugate base that registers the change of pH when small amount of acid or base added to it. How they're doing it? OH minus converting to H2O, creating A minus. A minus, so when you're adding the base, small amount of base, when you're adding the small amount of acid, A minus is converting to HA. So by going back and forth, it is maintaining a proper pH inside the cells or inside the blood or any kind of solutions that you talk about it. So that's the buffer. And this reaction that I'm showing you, it is called buffer capacity. Buffer capacity. Buffer, B-U-F-F-R, buffer capacity. All right, buffer capacity. CA capacity. All right, buffer capacity. So buffer capacity is this is the one. This is cycle that you saw it. HA converting to A minus is converting to HA. When you add a small amount of base, a small amount of acid. Small amount of acid. How much time do I have? Let's see. Yes, how much time? Oh, hello. I have only 6 minutes. You're reducing. That's fine. All right, let's go. All right. So now let's see how does it maintain. How can you determine How can you determine what is the relationship between pH, pKa, and its conjugate acid base, conjugate base or conjugate acid or weak acid. So that's basically the relationship we're going to develop it. And how does it develop? So basically, HA, weak acid, plus water, H3O positive plus A minus. So one can write the K equilibrium. So K equilibrium, K equals, remember the equilibrium we talked about earlier? So concentration of hydronium ion, parenthesis, right? Concentration of hydronium ion, please write down, third parenthesis, concentration of hydronium ion multiplied by concentration of A minus. Everybody okay, right? Concentration of A minus divided by concentration of HA, undissociated acid, HA, plus concentration of water, plus parenthesis close, concentration of H2O. Everybody okay, right? This is the equilibrium. When any reaction is equilibrium, like reversible, then you have to write the equilibrium constant K equal concentration of hydronium ion, this concentration of A minus conjugate base divided by the reactants, concentration of weak acid multiplied by multiplied by concentration of concentration of water. This water. Water, remember the water is a constant. We talked about earlier. Water is very constant. You have too much amount. So if we multiply the K times water, concentration of water. So K times water. So basically, within the K multiplied by concentration of water, H2O, concentration of H2O, all right, and that equals Ka. What's the Ka? Ka, please write down, Ka equals, K is the dissociation constant of a weak acid. So this is the dissociation constant. Dissociation constant of a weak acid. Dissociation of a weak acid. Dissociation constant of a weak acid. So dissociation constant, all right, constant of a weak acid. All right. So that's a Ka, and that's a K equilibrium multiplied by concentration of water is a Ka, and that is equal concentration of hydronium ion multiplied by concentration of conjugate base divided by concentration of conjugate undissociated acid. Now, if we take the negative log from this side and the negative log this side, ultimately after solving this equation, you can come up with equation called pH. pH equals pKa plus log of A minus divided by concentration of HA. So pH equal pKa, you know the pH, negative log of concentration of hydronium ion. pKa is a negative log of Ka, negative log of Ka. So pH equal pKa plus log of A minus divided by concentration of HA. This is known as Henderson-Hasselbalch equation for a buffer. Henderson-Hasselbalch equation for a buffer. This equation you must remember, because I'll ask the question from this. I will give you the tomorrow, Wednesday, I'll give you some example and to how to solve it and how to calculate the pH of a particular weak acid when it is dissolved in water. All right, I think my time is up, I believe. All right, okay. All right, no, I still have 2 minutes. I'm not going to let it go on. All right, so I'm going to ask you, so how to calculate the, sorry, let's go to the one more time. Let's go to the how to calculate the pKa. So pKa, let me give you the equation. So Ka, let's say just Ka example, Ka of acetic acid is 1.85 times 10 to the power minus 5. 10 to the minus 5. Now, who can calculate the pKa? Can you calculate? So, Ka, dissociation constant of an acetic acid. Dissociation constant of an acetic acid. Dissociation constant of acetic acid. Acetic acid, vinegar, huh? Acetic acid is 1.85 times 10 to minus 5. What is the pKa? Who can calculate for me? pKa. So pKa equals negative log of Ka. Negative log of Ka. And that is equals negative log of the whole thing. 1.85 times 10 to the power minus 5. Can you calculate for me? Who can calculate? Let's see. So pKa is a negative log of K. Just like pH. pH is negative log of concentration of hydronium ion. Can you calculate for me? What's the pKa?
Is it like 4.73 ish?
Wow, wow, excellent. Very good. Yes, it is. Yes, it is. It's a 4.73. 4.73, 74 doesn't matter. Yes, yes, it is. All right, so he knows. Rest of it, practice it. If not, we'll talk about Wednesday, okay? 4.73, that's what he said. Yes, very good. Yes, it is. Yes. So pK is a negative log of K. So pK will be given to you. And also I'll give you the concentration of A minus, concentration of HA. And from that, you have to calculate the pH of a buffer. It will be in the test, one way or another. And you have to know how to calculate the pKa. You have to know how to put it, put all those parameters into the equation, Henderson-Hathaway equation, to get the buffer of a solution. I'm going to stop here for today. If you have any questions, I'm all yours, okay? All right. And by the way, everybody did very well in the test. If someone did not, I told you earlier, I think. If you did not, but definitely keep working. But everybody did very well for the first test. Second test may be a little harder, depending on the components, the topics that we have. All right.